Hello everyone, and welcome to the first of our Fault2SHA Learning Series that will be taking place on the second Monday of each month at 3 p.m. Central European Time. I'm delighted today that Lucilla Benedetti is going to be kicking off the series. Hello everyone, and welcome to the first of our Fault2SHA Learning Series that will be taking place. I'm getting feedback from YouTube. We are live on YouTube, but delayed by a few seconds. So that was showing that it worked. And Lucilla today is going to be talking about cosmogenic nuclides as a tool for constraining rates of deformation. The second session in this series will be on the 8th of February by Francesca Cinti, who will be talking about paleoseismic studies in hazard modeling. So that will follow on from today's talk. For those of you in the Fault2SHA community, Lucilla Benedetti doesn't really need an introduction, and I want to really dedicate as much time to her as possible. But I think it is just worth noting that she has over 70 publications in internationally peer-reviewed journal. She has over 2,350 citations in over 1,500 papers. So she is certainly influencing a lot of science out there. So we're absolutely delighted that she is going to give our learning today. And I'm going to hand over to Lucilla and she will tell you how she's going to run today. And I really look forward to learning a lot. So thank you, Lucilla.
Thank you, Joanna. Thank you all for being here. So I'll start sharing my screen. And so, yes, as Joanna told you, I would like to, it's a great pleasure for me to start this learning series, Fault2SHA Learning Series, by introducing you to cosmogenic nuclides, more specifically, cosmogenic nuclides as a tool to constrain rates of deformation, because we thought this would be the most appropriate for our group Fault2SHA. So because I would like this learning series to be as interactive as possible, and I won't be able to see the chat, I really would like to ask you to interrupt me. Don't be shy, just do it if there is anything not clear. If you have questions, I think it will be much more pleasant for everybody if there is some, so feel free to interrupt. Of course, I will try to leave of course some time after also for exchanging together, but don't hesitate to interrupt. Okay, so let's start. No, it's not changing. Can you see the next slide? Yeah,
it's on your introduction slide.
Over the next 45 minutes or the title?
No, it's still on the title slide at the moment.
Okay. And I wonder why. Okay, let me try again.
That's working now.
Okay. And if I'm changing the slide, you see them changing?
Yeah.
Okay. For the next 45 minutes, the objective is to present you some of the important theoretical aspect here on the right side. You see my mouse moving also? Yeah?
Yes.
Okay. So the theoretical and practical aspect of cosmogenic nuclides, and we will review also some application of those cosmogenic nuclides to passive and active markers. I will define what I intend by that after. I was also thinking of presenting you aspect related to denudation rate, but while preparing the presentation, I realized that I wouldn't have enough time, and I think this probably deserves a specific learning series that we could have if you think it's useful to you, denudation rate and aspects related to uplift rate determination. So I won't be seems that okay. I won't be learning about this. You see the next slide, just to make sure, and then yeah.
Yes.
Okay. Okay, so why do we need cosmogenic nuclides? Because the Earth's surface is at the interface with many different processes like tectonics, climate, and topography. And if we want to be able to better understand those processes, we need to study surface processes that will be able to tell us something about actually tectonics and climate. For example, a morainic deposit is allowing us to know better about how climate works, or assessing how the fault slip is able to tell us something about tectonics. And so to be able to understand the surface processes, we need to have a specific chronology dedicated to those surface processes. And this is where cosmogenic nuclides enters, and you're going to see why. Okay, so first, what is the source of production of cosmogenic nuclides? It is cosmic rays. So cosmic rays are originating mainly from supernova explosion, and are mainly protons, very high energetic particles, and primary cosmic rays are protons. And then those protons interact with the matter that they come through to produce neutrons, which are the secondary cosmic rays. So mainly entering our atmosphere, we're going to have neutrons. And also we're going to have about 2% of muons. So those names, neutrons, muons, are high energetic particles, and they are defined by their level of energy, which is what you see here. Here you see a graph showing you the neutron energy that is entering our atmosphere. And what you see is that you have different type of neutrons depending on their energy. So you have high energetic neutron, fast neutrons, and what we call thermal neutrons, which are much less energetic neutrons. And this energy dependency is important to understand, because it's what is going to drive the reaction then that are going to affect the surface of the Earth and produce cosmogenic nuclides. So cosmic rays, here you have an image of a solar flare. So I said they're mainly coming from supernova, but you can also have them from solar flares. And this is just an image to show you how those cosmic rays actually interact with the matter in our galaxy, but also with fields, and in particular for the Earth, the geomagnetic field. You see here the rays that are deflected by the geomagnetic fields. So to summarize what I just said, so cosmic rays interact with fields. So in our, here for the Earth's geomagnetic field, they also interact with matter. So with all the elements that constitute our Earth's atmosphere. And when they reach the atmosphere, they're going to interact with the elements that constitute the Earth's surface. And this is going to allow the production of cosmogenic nuclides and in situ into the rock. What I want you to understand is that in this table, I'm presenting you the most commonly used cosmogenic nuclide. And what you see is that the cosmogenic nuclide, for example, beryllium-10, are dependent on the type of reaction. So spallation reaction are caused by high energetic neutrons onto silicium and oxygen, so SiO2 quartz. This is going to produce beryllium-10. For example, for chlorine-36, we've seen that, so there is high energetic neutrons that are going to produce spallation with calcium. So calcium-40 impact by high energetic neutron is going to produce chlorine-36. But you're also having less energetic neutrons like thermal or epithermal neutrons, as I've shown you on the slide before, with chlorine-35, capturing a neutron from those less energetic neutrons, will also produce chlorine-36. So this table is important because it allows you to understand that the cosmogenic nuclide production depends on the type of reaction themselves depending on the energy of those particles and on what we call the target element. The reason why those cosmogenic nuclides are called then cosmogenic nuclide, you understand, is that because they are only produced by the interaction of cosmic rays and certain elements in the Earth's surface or in the atmosphere. Chlorine-36, for example, is also produced in the atmosphere by argon. Some of those elements, like again, chlorine-36, can also be produced anthropogenically. For example, very high energetic neutrons produced by nuclear power plant can also trigger production of anthropogenic chlorine-36. Okay, so what's important then is to understand what's behind this production, this in situ for us, doing rates of deformation. It's important to understand what's behind this in situ production. Any question at this point, or? Okay, I'm going on. Okay, so now what's going on exactly at the surface? So we've said there is a source, which is the cosmic rays. We said mainly neutrons. And those, I'm just going back. So we said that those high energetic particles are attenuated by whatever matter they enter, they interact with. And this is the case at the surface. When those cosmic rays enter the surface and interact with the matter in the rocks, they're going to be strongly attenuated. So basically, the amount of cosmogenic nuclide produced as the Earth's surface, it's like suntan. That's why I'm putting this very nice picture of this cat taking sun. It's exactly like this. It's like if you, whatever process that will bring a rock exposed to the surface, this rock will start accumulating cosmogenic nuclides. If something buries, if a process buries this rock under a certain amount of matter, it will not produce cosmogenic nuclide anymore because those cosmic rays will be attenuated. So this transfer into this graph here that you see, which is the chlorine-36 number of atoms produced per gram of calcium per year against depths. And here you have the total production here with depths. And you see that the production is majority at the surface and decrease exponentially with depths. So this is really key to understand that you have this exponential decrease of production at depths. At about 50 centimeters, you will have already lost mostly 50% of this production. So then you will have some losses due to the fact that most of those cosmogenic nuclide are radioactive, so they disintegrate. So as much as you accumulate, you will lose due to the radioactive decay of those cosmogenic nuclide. And you will also lose those cosmogenic nuclide because your surface will evolve, will be denudated with time, and you will lose the first amount that you've accumulated at the surface. So this can be translated into the equation that you see here, which explains mathematically the link between the concentration of a cosmogenic nuclide and those different parameters, in particular T, the exposure duration, Z, the depth, and epsilon, the denudation. This term is for eventual inheritance. You could have some amount of cosmogenic nuclide that has been accumulated prior to the exposure that you're trying to calculate with this concentration here. This is the half-life, and this is the attenuation length, translating this effect of exponential decrease. So this equation, if we assume no inheritance, can be simplified into this equation, which is the basic of the relating the concentration with time and denudation. Okay, so now let's go to the production rate. So as you've understood, this term is very important, and it is related, as I said before, to the target element of the sample. So here for beryllium, oxygen and silicium, so quartz, bispallation reaction. And for chlorine-36, you have several pathways of type of reduction that are listed here. And what you want to know in your sample is the amount of beryllium-10, for example, produced per gram of quartz per year. Or for chlorine-36 in your carbonate rock, the amount of chlorine-36 produced per calcium per year. But of course, it's important to be able to understand this, that you take a sample that has only one single target element. For example, here with this basalt, this is a trachy basalt, and you see that you have phenocryst and you have a glass. In the phenocryst, you're going to have calcium and potassium. In the glass, you're going to have calcium, potassium, and chlorine. If you take these samples as a whole rock, you dissolve this sample, you extract the chlorine chemically from this sample, and you measure the chlorine-36 in this sample. How are you going to deconvolute the different pathway, the different production of this whole rock? You're going to be able you're gonna need, the full chemical composition of your sample to really be able to understand how much calcium, how much potassium, how much chlorine you have in your sample, and to relate this amount to the specific production rate of calcium or of potassium that you know through calibration studies. So it's very important to understand that a production rate is only linked to a certain target element and to a specific production pathways. And over the last 20 years, there have been enormous progress on those calibration studies. So isolating a target element, for example, calcium using carbonate, trying to find sites where you independently know the exposure range and measure the concentration and deduce an amount of atom of chlorine-36 produced per calcium per year. I would like to cite two initiatives that have been very important because they are a bit similar to our Fault2SHA community. In the years 2003, 2004, when many people were starting to use cosmogenic nuclide, we realized that it was very important to get together and to really sit to make the systematics of all those cosmogenic nuclides much more accurate than it was at that time, and in particular, the calibration studies. So I'm going to show you an example with chlorine-36 of those calibration studies. Okay, so to summarize what I just said, so for chlorine-36, for example, you've understood that you could have three sources of production, mainly. You can have through high energetic neutron bispallation reaction of calcium production of chlorine-36. You can have through less energetic neutrons, the low energetic neutron, the thermal neutron capture of chlorine-35, capturing a neutron to produce chlorine-36. And you can have the slow negative muons that will be captured by calcium and potassium to produce chlorine-36. So if you look here, this is a graph showing you the same as before, atoms of chlorine-36 per gram per year per depth. And this is to show you how the chemical composition can affect your production rate, and also this exponential decrease that we assume for spallation. But here what you see, so again, this is the total production, and in yellow you have the spallation production, so this production from calcium of chlorine-36. This is for a sample that has only 10 ppm of chlorine, which is regular for let's say a carbonate sample. If you go, for example, into a basaltic rock and you look into the glass of the basaltic rock, you could have a very, very high chlorine content, such as 500 ppm. And you see that the production, the different production here are very different, because it's not the spallation, which is the dominant one, is the one from the lower energetic neutron, the one produced from natural chlorine. And you see that the shape of this decrease is very different than the one from spallation. There is a peak at about 50 centimeters. And of course, this is going to bring a lot of uncertainty into your result of exposure age. So that's why in most cases, when we have a very high content chlorine in our sample, we avoid those samples, because this pathway by low energetic neutron is poorly known and triggers a lot of uncertainty. So we try to avoid those type of samples, to take samples that are rich in calcium or in potassium and low in chlorine, to minimize this pathway of production. So the chlorine 36 concentration is going to be proportional to the exposure age and to the different production here that you see here, and that you need to know, of course. So to be able to determine an exposure rate, you're gonna need to know all those different production rates. So how do we know those different production rates? As I said before, by calibration study. And here is an example that we've done with one of my students in 2009. And so what we did at this time, so the reason why we did this is because at this time there was a big discrepancy, big discussion on the use of chlorine 36 for exposure age. People were thinking chlorine 36 was not a reliable tool, because actually the production rate that you see here you see the 3 production rate that at this time were mainly used. And you see that there was a huge discrepancy on those production rate, more than 20% of discrepancy, that of course then is going to propagate into uncertainty in your final exposure age. So we've explored this problem with Irene Schimmel-Fenning, and what we did is that we choose to work on lava flow that were independently dated by potassium argon. The great ability of lava flow is that their depositional rate is equivalent to their exposure age. So it works very well with potassium argon age. And we pay particular attention to minimize the pathway for the production pathway by chlorine. And so what we've observed is that in those 2 studies where the production rate was particularly high, actually it was a whole set of samples that has been used at this time with very variable chlorine concentration. Some of them had very high chlorine content, but they were the chlorine 36 that were in those samples was attributed to calcium spallation, while it was due to the production of low energetic neutrons. So that's why the production rate here of calcium was particularly overestimated compared to the study that were isolating the calcium production pathways. And so we set up then at CEREJ a chemistry of extraction that would favor the target element extraction, so through phenocryst, so isolating calcium feldspar rather than working on whole rock or potassium feldspar, and of course limestone. Is that okay up to now, or any questions? Or
Lucilla, can I ask you, you mentioned the problem when you have different phenocrysts.
Yeah.
For chlorine. So does that mean you can only date it when there's only one type of phenocryst with chlorine, or can you deal with rocks that have different phenocrysts containing chlorine?
So you can deal with rocks having different phenocrysts, but you need to know the exact chemical composition of your whole rock. You need to know how much calcium, how much potassium you have. You're going to treat this as a whole rock, basically. like a big mix of calcium, potassium within your whole rock, but you need to know exactly how much you have in all of them.
Thank you.
Any question? Any additional questions? Okay, so let's continue. So then those calibration studies define the production rate at a specific site, and you need to be able to use them to scale them at your sample site. Why do you need to do that? You need to do that because, as we've seen before, those cosmic rays interact with the matter they cross. And so the production rate is not going to be the same if you're at the surface or if you are 2,000 meters of altitude, of course, because at 2,000 meters of altitude, your cosmic ray will have interact much less with matter than 2,000 meters below, because they will have met many other elements in the atmosphere. So the decay, the atmospheric decay, the atmospheric attenuation will be stronger at the surface than at higher altitude. So production rate is going to vary with altitude. It's also going to vary with latitude because of the geomagnetic field, because the geomagnetic field is deflecting your cosmic ray, and this deflection is less intense at the pole than it is at the equator. And because the geomagnetic field has intensity as vary with time, if you have a less intense geomagnetic field, you're going to have much more cosmic rays that are going to be able to enter our atmosphere, so production rate will be higher. And if you have a low geomagnetic field intensity, it's going to be the contrary. So the production rate can also vary with time. So you need to scale those production rate to those different variables. And you also need to scale to specificity of your site, and in particular to shielding effects. So what are shielding effects? Simply the fact that your sample rock can be shielded by a topography, and again, always with the same idea. Cosmic rays are going to have to go across this matter of rock, this topography, to reach your sample, and so are going to be attenuated. So of course the production rate will be half, more or less, in this example here, or 70%, than if you would have the whole sky free of any topography around your sample. So this is the shielding effect, and you can have shielding effect also due to some snow cover or vegetation, any things that is going to cover your rock and shield it from cosmic rays. For all those different scaling, I will talk about this also after. You have scaling schemes that have been available. Our colleague Nat Lifton has been working a lot on all the scaling scheme related to latitude, altitude, and time, again within Cronus initiative. And for shielding aspect, you have also several articles that provide you some elements that you can use to calculate those shielding effects. Okay, so now let's see what is the time window for those different cosmogenic nuclides. So here I've put again the equation that we've seen before that tells you the link between concentration, time, and denudation. And here on this graph, what you have is the concentration of beryllium against time. And what you see is that after a certain amount of time, you reach what we call a steady state, meaning that you reach a moment where all the beryllium-10 that is produced is going to be compensated by the loss of this beryllium-10 due to radioactive decay. And if you have, this is also dependent on the erosion or the denudation of your surface, because of course, if you have no erosion, your surface is pristine, is not going to move, and you are going to be able to accumulate beryllium-10 over the time until you reach this equilibrium in a much longer period of time, in this case about 1 million a year. Then if you have a very high denudation rate that is going to remove matter on your surface, then you're going to be able to determine an exposure age of your surface on a much shorter period of time. And this is depending on the decay of your element. So for beryllium-10, you are going to be able to determine the exposure age of a surface over 1 million, 2 million years, depending on the denudation rate, because you're going to, this is the time before which you will reach steady state. But for chlorine-36, because the half-life is lower, it's more around 600,000 years that you're going to be able to work on this exposure age. This is also translated into this equation. If you assume negligible erosion, then you can assume a linear increase of your concentration.
We've lost you, your microphone. If you could just come a bit closer again.
Sorry, you lost me?
Yep, that's better again.
Okay. So I don't know when you lost me.
About 20 seconds.
Okay. So what I was saying is that if you assume denudation is negligible, you have a linear relationship between the concentration and the exposure age, as seen here. And if you have an exposure age which is very, very long, much twice the half-life, then you're going to have your concentration, which is directly inversely proportional to your denudation rate. So this is interesting too, because on surfaces that are old enough to reach steady state, then you can determine the denudation rate of those surfaces. So to summarize what we've said before, you need to have several parameters to be able to actually derive an exposure age from the concentration of your nuclide. So we said the shielding factor, the scaling factor, the chemical composition, and the production ways, the different production ways from the different pathways. So you need to have all this to be able to determine an exposure age. Of course, you need to get the concentration of your sample, and you do this by accelerometer mass spectrometry measurement. I'm not going to go into the detail of those measurements, but just for you to understand that it's a very highly precise measurement. Just imagine that for one nuclides of chlorine-36 in the accelerator, there is this amount of the natural chlorine-35 elements, and what we call the isobar, sulfur-36, which is the main reason why we're using accelerator mass spectrometry, is that we need to separate the chlorine-36 from its isobar, sulfur-36, which is naturally in nature. And so you have a lot of sulfur-36, and so the reason why we're using accelerator is to separate from those two. Note those elements related to the uncertainty that we get from. So basically, we measure 10 to the 6 to 10 to the 7 atoms of chlorine-36, and to be sure that you have a measure which is accurate, you would need your blanks, your chemical blanks, to be at least 100 times lower than what you're trying to measure. If you want more detail and all those aspects, chemical extraction and also IMS measurement, and also on what I've been just talking up to now, go to this book, which is very well done by people using the EU initiative, and don't hesitate to contact me. You have my email. Okay, so you've understood that the exposure age calculation is a complicated and dense procedure, as you've just seen. And you can do numerous choice, in fact, of parameterization. For example, for the scaling, you can have different type of model that you can use. You can have different production rate that you can use. So because of that, there are several teams that have been proposing exposure age calculator on the internet, but also through papers. Here, I'm just showing you one example. It's a CREP calculator. And most of those calculators have more or less the same scheme. So you can choose through the different parameters. So for example, the different scaling scheme, the different atmospheric model, or the geomagnetic database. Now you will understand why. You then load your sample characteristics. So all the aspects related to the IMS measurement, but also the chemistry, as we've seen of your sample. And then you decide on which production rate you want to use. You can use a production rate that has just one value that has been calibrated very close to your sample size, because then you avoid uncertainty due to scaling scheme. Or you can choose to take a more global mean, which is an average of all the production rate that have been calculated over the world, for example, for barium-10. So you can choose among those different aspects, and you can also then compare how this is going to affect your uncertainty on your final exposure range. And then those calculator will yield the exposure range, and you can then present this exposure range on a form of a PDF. We're going to see this after. Those are very, very useful and very well done. Okay, so now let's go to some example for for our topic, which is rates of deformation. And the most important things is the sample strategy. As you've seen, the process of production of cosmogenic nuclides is complex, and what you really need to do is to be able to determine what type of process you want to unravel. So for this example here, this is an example of what we call a passive marker. So you have there are some fluvial terraces that have been deposited, abandoned, and offset. And so you can use those markers, for example, the green fluvial terrace here that has been abandoned, so will not be affected by any depositional effect. That's your hypothesis. After the motion of the fault, and determine the exposure range of the surface, passive marker. You can also work on active markers, so markers that are actually still moving with the fault, but you can assume that the process related to the kinematic of these markers can be chronologically determined through cosmogenic nuclide. So we're going to see an example of this passive marker and active markers. What I want to emphasize here is that the type of surface that you are going to choose, for example, for your sampling is crucial. In other words, we are doing more for chronology. We're not only doing chronology or morphology, we need to do both. Why is that? Because if you choose, for example, to work on a field terrace, meaning a terrace that has been deposited by a very important aggradational event that you can assume as occur at a single moment of time over a very short period, it's different than if you decide to work, for example, on a strass or a cut terrace, or you can say an incisional terrace, because then the deposit below could have been exposed for a much longer time before the event that you are trying to date. The same applies to colluvial. Can you assume that all the pebbles of your colluvial have not been exposed prior to the emplacement of this this alluvial fan, for example? So all those are questions that you really need to ask yourself before going and sampling for cosmogenic nuclides. So before sampling, you need to understand what is your purpose, what do you want to date, what type of deposit is that, can you assume already the history of emplacement, processes behind sampling. And very important, where are you going to sample? I mean, ideally, you should have an accurate map of the identified markers that you want to date before you go into the field. This would make you save a lot of time, actually. Okay, so let's go to some examples. So example of passive marker. So passive marker is, as I said before, you assume a single aggradational event like this event in placing this surface here, T0. And then because of climate change, this terrace is incised after being aggraded. And the fault offset this surface and somehow preserve this surface from the next incisional event. And you can have like this a series of surfaces that are going to be in place due to change in climate phase, aggradational, incisional phase, and preserved due to the evolution of the fault. So those are passive markers. And so here you have a very nice example of those markers. You have this very nice fluvial terrace here that you see have been offset by the Coco-Chili rupture in 2001. And so you can go here on this surface and try to date the exposure age of this surface by collecting pebbles on the surface and determining the exposure age of those cobbles. So each red curve here is one exposure age of one cobble, and you can have a PDF probability density function showing if all those different age merge into a single age that converge into a single age with a certain uncertainty that is the shape, the width of your Gaussian here with all your different sample here. So this is called camel plot, and you can find many MATLAB routines allowing you to produce those typical camel plots. So this is almost a perfect result here, but of course it's not that simple most of the time. Most of the time you can have what we call outliers. So you can have a pebble that arrive here with maybe affected by pre-depositional effect or post-depositional effect that is gonna make this distribution wider and maybe more difficult to interpret. So that's why this whole process of thinking how this surface has been deposited before and what you can assume in terms of post and pre-depositional processes is very important. So this is good, but the problem with this approach of only sampling surface sample is that you have a strong assumption on denudation, because of course you don't know the denudation here, and you can only assume negligible denudation to derive your exposure age. Any questions on this?
Lucilla, you just mentioned that you have to assume negligible denudation. How important is that if you get that assumption a little bit wrong?
But what you can do, what we usually do, is that we make tests. So we assume a certain denudation and we see how much our exposure age is gonna change. Usually for Holocene deposit, it's very small, the uncertainty, because if you remember the graph where I was showing the linear increase, when you have a surface that are very young, the effect of denudation is going to be very small. Of course, if you're dealing with an old surface, then denudation is going to be an important uncertainty. So you need to bracket your result by testing several couples of exposure age and denudation. Another way of doing would be to do depth profile, which is this example here. So to do depth profile is very useful, for example, when you have a surface that has been affected by a soil, or where you don't know if your surface has not been affected by certain post-depositional processes. And so you dig basically a hole of at least 3 meters, because you want to make sure that you go up to the most important level of exponential decrease to really well resolve your depth profile. So depth profile will allow you first to understand whether your surface has been stable after emplacement, because if there have been some removal or anthropogenic problems, then all the sample will be all messy. So it's very important. And also because it allows you to actually determine both the couple exposure age and denudation. So how you do that? You do that by inverting actually your data. So this is an example here that have been done by my colleagues here at CEREJ, but you have more recent example here in 2017. And most of those examples have gone through inversion modeling through Monte Carlo Markov chain algorithm. So basically they try to minimize the difference between beryllium or chlorine-36 data of that profile, the points that you have here, and synthetic profile with various couple of exposure age and denudation. And what this paper, for example, show is that while for each of those samples, you're going to have several couples of T and epsilon possible for the whole profile, because the surface has experienced the same history, you're going to have a single solution actually that is going to be able to fit all your data all together. This is what you see here. The Monte Carlo inversion converge basically into a single solution. It's not that you have another convergence here or here. You have basically a single solution. So depth profile are very powerful because they allow you actually to not assume anything on denudation rate, but actually resolve the couple. So now most people do actually depth profile. Okay, so now active markers of deformation. So the one example of active, of course, is false carp. So what you have here is the 2 meters that have been exhumed over this fault plane here after the 2016 earthquake. So it was previously buried under the soil here and exhumed by the earthquake during at the moment of the earthquake. And so all the part above can be assumed to have followed the same processes. So this is an active marker which exposition is directly related to the process that you are trying to date, which is in this case, for example, the fault slip rate or the age of the different event that have triggered the exhumation of this portion or of the portion above. So exactly as we said before, if you want to work on those type of marker, you need to make sure that the processes that you are trying to date is related to fault slip and not to anything else, like, for example, in this case, erosion here, or erosion also here. So it's exactly as for a surface in a way. It may appear more complex, but it's exactly the same approach, actually. Always think that the process you want to date is related to what you're actually trying to date. So avoid going into places where you cannot make this assumption, basically. And so then the idea behind is again similar. What you're trying to do is to build a scenario of what could have happened to this marker. So in this case, we assume that prior to any exhumation, you had a surface, a simple surface, which was accumulating chlorine 36 with a depth profile, and then one event occur, and so this part is exposed and start to accumulate chlorine 36 at a constant rate, and etc. over the course of the life of this fault. And then exactly as we've seen for depth profile, you can collect some sample on those fault scarp. Those are all the points that you see here, and try to determine by inverse modeling the best fit between a scenario that is of course more complex than in the case of the depth profile, because it's not only one exposure and one denudation rate. It's a series of events or the slip rate of your fault. It can be various aspects, but basically that's what you do. So to do this, you need to build scenario based on certain assumption, what age, or what the sleep, or what's the long-term sleep rate that you assume, and you produce synthetic profile as the one that you see here in red, according to a modeling, knowing all those different parameters that we've seen before. So here, as I said, the scenario for fault scarp is more complex because the processes that have been exposing those markers, those scarp, has different phases. You cannot just assume no exposure, and then nothing. So they have been different phases. For example, here on this fault plane, what we see is that probably we can assume that we had a surface, just a single surface before, so with a depth profile like this. And then we exposed this scarp here. This part was probably more eroded because it's a diffusion profile. So we cannot get sample from this part, but we can get from this part. And this is exactly what we say here. We have a previous depth profile with no exposure, and then we built the exposure through time by testing different scenario. You can have other examples. So this is the example I was just mentioning. So an initial surface that has been exposed for a long time before the fault actually starts to move, basically. So you assume a surface with a certain denudation accumulating chlorine 36 for a certain amount of time, a quiescent fault, let's say. And then the fault start, and this is what you want to unravel. Or you can assume this is the most case that we have, that and this of course it's something that you based on your observation, on your field observation, where you're in this case or where you're in this case. If you have observation that you have a long-term cumulative displacement, it means that this fault has been active for a long time. And so you need to assume a certain long-term slip rate prior to the fault plane that you sampled. So this is what we do here, and the Monte Carlo Markov chain algorithm has been very powerful to help us unravel this, and has been used by several teams. So this is one example that I'm showing here, but there is also the group that has produced other type of modeling, but it's basically the same in the sense that we all end up with the same with the same idea behind, is that you can produce several scenarios that you test against your data. So here, what I'm showing you is a synthetic scenario. So basically, we're telling the modeling, we're giving this as a data set, actually. And in black, you get what the inversion is calculating as the best model. And you see that in this case of a characteristic earthquake scenario, it's doing actually a very good job over this part, which is the part where we do actually provide some data set of chlorine-36, and in here, no data set because it's the part that is eroded. And so you see that here on this part, it's not doing a very good job, although it's still rather good in giving a certain time window, which is accurate with what the synthetic scenario was. And this is another example with now a cluster synthetic scenario. So many events in a very short amount of time. So a very important period of active deformation, and then a quiescent period, and then another one very high level of deformation with several clustering events. And here again, you see that the modeling is actually doing quite a good job in showing us this clustering period. It cannot decipher the single event, but it can decipher an acceleration, a very strong acceleration versus deceleration, a quiescent moment, and a rather good also with a much higher uncertainty, of course, for this upper part. So so this is what can be produced using inversion modeling and chlorine-36 on active markers like Fault2SHA. Another example, and this will be my last example before the conclusion, is a recent application that we've done on the facets, triangular facet like this one here. So triangular facets in a way are similar to Fault2SHA, and you see the Fault2SHA here at the base. And what we've done here is sampling this triangular facet and assuming that the chlorine-36 buildup of this facet was similar to this modeling here, that you have a two-stage kinematic phase. So a first phase where the sample travel at depth with a rate that is similar to the slip rate of the fault. And the second phase, when the sample is exposed at the surface during post-glacial, when the scarp is exposed, that accumulate constantly chlorine-36 at the surface. And so by inverting the data with such a two-stage kinematic scenario, you see the data here in black, and you see the result of the modeling here. We can determine a slip rate for this fault over the long term of the age of this facet, that is around 100 Ka, 100,000 years. So this is a sort of exploratory, let's say, application. Here you have the facet, and here you have the sample that we can do on long-term markers of the deformation. Okay, so as a summary, what we've seen is that we have various sources of production for cosmogenic nuclide, but it's mainly new transpilation. New transpilation are strongly attenuated with depth, and so you can assume that the concentration of nuclide is proportional to the exposure rate, provided that you know the production rate. Chemistry allows extracting the target material and the cosmogenic nuclide built up in it. AMS measurement, accelerometer mass spectrometry measurement, allows measuring the nuclide concentration. The nuclide production rate has to be known and scaled at sampling site to derive an exposure range. I've shown you an example of online calculator, this one, but you have several ones that I've listed here. Note that this one that I've shown you is mainly for beryllium and helium, but soon we are working on a version for chlorine-36. Those other are available for both elements, and you have this Excel sheet also that you can use if you don't like online calculator, if you want to have all the equation for chlorine 36. Summary 2, more related to application. So we've seen that sample sites for rate of deformation should be well mapped, and processes behind their deformation have to be well understood and studied. For passive marker, it's important to ask yourself, can you assume no post-depositional processes? And as much as you can do depth profile that will allow you resolving both the exposure age and the denudation. For active markers like Fault2SHA, you have to ask yourself, can you assume the markers emplacement is a proxy of the fault kinematic, or is it related, is emplacement, is it related to any processes, any other processes? And you can test different scenario of markers kinematics with inversion model. Thank you very much.
Thank you very much, Lucilla. Does anyone have any further questions? I know I was asking them throughout. Is there anyone else who'd like to ask a question of Lucilla? Just have a couple of minutes.
Sorry, I was a bit long.
This is Paolo. Can I ask a question?
Hi, Paolo. Yes.
Thank you, Lucilla. Very nice lecture. Very nice lecture. Let's assume I would like to date a terrace, a passive marker.
Mm-hmm.
And I have cobalts, for example, containing quartz, and cobalts in with limestone. What would you suggest to date? With beryllium or chlorine or both? This is
I would suggest to do both. Why? Because the quartz and the carbonate might come from different watershed, and it's important if you date both because you will be able to test whether your surface has a single exposure history, I would say. So as much as you can, I would absolutely do both.
And how many samples if you dig a trench in order to build the depth profile? How many samples?
For the depth profile, you need to have a big density of sample over the first meter, I would say. So I would take a sample every 30 centimeter, because you've seen that the decrease is rather fast over this first meter. So you want to have more sample on this first meter, and then you can take a sample every 50 centimeter. Over 3 meters, it's okay.
Thank you.
I have a question. Stefan speaking. If I remember well your first slides, it's the helium is usable for every kind of material, of target. Is it possible to double any, I don't know, chlorine or beryllium with helium?
Sorry, what do you mean?
Helium. I don't know how to pronounce in English. Helium.
Yes, helium. Yes.
Helium is.
Well, yeah.
It's possible to use for each target, no?
Alors, no. The helium is mainly. Helium. The difference with helium is that it's a stable element, so it's accumulating and accumulating and accumulating because it's not decaying.
Okay.
Okay. So its applicability is, I would say, less for exposure age as we do for rates of deformation, because if you have surface processes that are overlapping each other, it will be very difficult for you to deconvolute the different processes. because it has been accumulated without interrupting, basically.
Okay, thank you.
Lucilla, there's a question from Haibo Yang in the chat, and they ask, could the cosmogenic nuclide also be used for dating bedrock thrust fault surface? If yes, how should we consider the sampling and the inheritance? Any suggestions?
What's the question? Frost fault?
Could the cosmogenic nuclide also be used for dating bedrock thrust fault surfaces? And if yes, how should we consider the sampling and the inheritance? Do you have any suggestions?
I'm not sure I understand what bedrock frost fault surfaces or bedrock frost?
Thrust fault surfaces, reverse faults.
But so for reverse fault, I would say, but why frost? Why it's important, this term frost? I mean,
I think it's reverse fault.
Ah, okay. To date reverse fault. I don't see it on my chat. Yeah, I mean, if it's reverse fault, it's the same. It's the same approach as for passive marker. You need to find surfaces that have been affected by your fault. For example, there are applications with folded surface, surface that have been deposited, abandoned, and folded by a thrust or a reverse fold. And if you can find such markers, that's great to date the rates of reverse or thrust fault. But the idea is always the same. You need to identify markers that of the deformation you're trying to unravel, I would say. Does it answer the question?
I think so. We have a
question. Bedrock thrust fault. Okay, I see it. Bedrock thrust fault. I don't have an image of this in my mind, but yeah, probably. I mean, if the idea is that it's the exhumation is related to the motion on the thrust fault, probably. As I would say, I mean, my personal experience is that when I'm in the field, I'm trying to find a site on which the exposure history is the simplest, I would say. If it's too complex, then you're going to have to assume many things, and you're going to add lots of uncertainty, I would say, in your final result. So the simple, so like the passive markers that I've shown you, emplacement, deformation, and then you go and you date is the best. But
thank you, Lucilla. Jenny Robertson has a question. Jenny, can you ask?
Oh, hi, Lucilla. Thanks for that. It's really interesting. I work on late quaternary wave cut platforms and do 36 chlorine dating on them. And we typically have quite high errors. So in the region of sort of 15 to 25%, which we work with fine because we can use the sea level curve. Aside from the role of the production rates and the uncertainties associated with the production rates, what do you think is possibly the next biggest contribution to those errors? Do you think it might be the water content or something else? I'm just trying to think of how we might be able to reduce them, probably more from an external point of view.
You mean the uncertainty related to your wave cut platform, right?
Yeah, so the age, we essentially use Cronus calc to calculate our ages, and so it takes into account all of our analytical and our external uncertainties.
Yeah.
But you know, we might have an error on an uncertainty on an age that's sort of 20,000 years, which I'd love to try and figure out how to reduce slightly.
Yeah. Do you have a high chlorine content in your sample?
So I can give you do have a high chlorine content.
In other words, what are the main production pathway, I would say, on your production? Because if, for example, you have 10 or 20% of your production which is related to natural chlorine, then it's going to be very difficult to lower those uncertainty. So that's the first thing. The second thing is analytical. What's the uncertainty that you have basically on your IMS measurements? You can have, you know, IMS that are producing data sets with 5 or 7% uncertainty and other with 2% uncertainty. And this then propagates and trigger much more uncertainty on your exposure rate. So as much as you can, you should try to do you know, a very clean chemistry on those samples, and very, you know, ask the people doing the measurements to count longer maybe your samples, so you reduce your analytical uncertainty. That would be my two first guess, I would say. Then WaveCut platform, I didn't mention them, but are very interesting markers actually. And I see more of those applications in the literature, and I think it's great. It's not easy because I think you have to assume that you didn't have production of chlorine-36 when they were submerged, let's say, before they emerge. And and so it can be tricky, but it's great.
Okay, that was really useful, thank you. I think our internal uncertainties are relatively low. We're doing, it's limestone, so I'll have a much closer look at our content of chlorine in terms of the external work.
And something also that could you know, is because in those WaveCut platform, if it's so it's WaveCut, okay, so it's limestone, it's not conglomerate, right?
Yes, it's pure limestone. We do the density checks, etc. We use mill holes and lithophagid borings to make sure we've got very small amounts of erosion, so we know we can constrain our erosion.
Well, I'm happy to exchange on this more directly if you want, and don't hesitate to.
Perfect. I'll pop you an email. Thank you.
Lucilla, there was a question in the chat from Alberto Pizzi. And it says, based on your data and experience, do you now prepend for a characteristic or cluster general model, or does each fault have its own history?
I think most of the fault, and I think the group of Gerald will share this conclusion, is that most of the fault we've been working on, the normal faults in the Mediterranean, have a type of cluster behavior, I would say, rather than the characteristic periodic event that we used to think, which would have been perfect for, of course, predicting better the event, but unfortunately it seems to be more complex than that. So I would say most of the faults we've been working on are like this, but it doesn't mean that this is the case for all of them. Probably very long and mature strike slip fault might have a more characteristic periodic way of slipping. I think each fault has its own history.
Thank you, Lucilla. We have Francesco Iezzi would like to ask a question, and then there's one more in the chat, and then after that I think we'll have to close, as I know people have places to go. But if we go to Francesco Iezzi, and then there'll be a question from the chat.
Hi, Lucilla.
Hi, Francesco.
Thank you very much for this lecture. It's nice and clear. Can I ask you a question on the fault scarp measurement that you've shown earlier? You earlier said that we cannot consider faults to be just buried and then, coming up, being exposed, and the chlorine growing as it is. But you showed that you include some inheritance in the chlorine content on the fault. So my question would be like, how do you actually quantify this inheritance? How do we, if I'm going to field, how do I quantify the inheritance on the fault plane?
The inheritance in the fault plane, meaning what I meant by the inheritance in the fault plane is the amount of chlorine-36 that is produced before the exposure of the actual fault plane that we are sampling. Okay?
Yeah.
Yeah. So the thing is that we don't actually assume anything for this fault inheritance. It is also a parameter that we include in our scenario, and that we derived basically through what we call the long-term slip rate. What we assume is that the chlorine, the chlorine 36 that we have in each of the sample that we collect is the sum of all those different chlorine 36 accumulated over time. And a part of this chlorine 36 is due to this long-term, let's say, inheritance. And so in the inversion, and this is also the power of those inversion model, we can make some a priori constraint on those long-term slip rate, for example, saying it's between 0.1 and 3, for example, millimeter per year. But that's the only thing that we do. And then what we also do is that we put an a priori constraint, because if not, the model will run independently, is that we say that the fault has started to slip, for example, 300 Ka ago, because we see the size of the facet. For example, it's 100 meter high, I'm saying, you know, and so assuming a millimeter, let's say, so it's gonna be basically a million year old or less. So we put a start timing, and we put a slip rate as a priori constraint. I mean, we put a range of slip rate as a priori constraint, and then that's it. Then one of the result of the inversion is this long-term slip rate, actually. Does it answer your question?
Yeah, yes, thank you.
It's actually, if just I can take 1 minute, it's shown here in the result that I've presented. It's this parameter. So you see,
Hi, Lucilla. A final question from the chat.
I was you heard me, because at one
No,
moment I was
no, sorry, I didn't hear it. I didn't hear anything after you shared the screen.
Okay, I was saying that I was just sharing my presentation just to show you. Do you see my presentation?
Yeah, yes, I see it now.
Okay.
Yes.
So you see the long term.
Yes.
The long term slip rate parameter is this one here. This is the what we call the periglacial. So that's also an output of the inversion modeling.
Okay. Okay. Thank you very much.
Thank you.
So Lucilla,
your question, Joanna, you were saying.
Yeah, your final question from Zhangji Zhu. And it says, in their study, the upper part of the bedrock scarp, and it's a limestone bedrock scarp, has lower concentration than the lower part. Could you have any idea to estimate the old events and deal with this case? They have identified 2 clear events by quantitative morphology of the fault scarp.
So the upper part has a lower concentration than the lower part, meaning that the profile is inverted related to what we would expect, because we would expect that the highest part would be the oldest and then the highest concentration, and we have the contrary. So either it means that the scarp that they are actually sampling has been, it's an erosional scarp, and not a scarp due to, you know, fault exhumation. I would say that's my only explanation. And you could still see in your scarp 2 portion, maybe as it's mentioned here with morphology, saying maybe a portion which is more clear and another more darker due to erosional effects. So I would say, are you sure that this scarp has been exhumed by fault motion? can you check that? That would be my answer.
Okay, well, thank you everybody, particularly to Lucilla, for giving a really interesting lecture. We had lots of people asking lots of questions, so hopefully everybody now knows more. And there were lots of further comments in the chat, by the way, about great talk and thank you. I just didn't read them all out. So thank you to Lucilla and to everyone for joining us. And we look forward to joining you next time on the 8th of February for Francesca Cinti, who will be talking about paleoseismic studies in fault modeling or fault hazard modeling. So it leads on from today's talk. So thank you everyone and see you then.
Thank you all.
Merci Lucilla, merci à tous.